bioactive, biocompatible, and biodegradable. There are several different types of bioglass, and one that's commonly used is the 45S5, which has the composition shown up here. There are many different uses for the 45S5 bioglass, such as bioglass scaffolds and implants, and a picture of a scaffold is shown on the bottom right-hand side. A bioglass scaffold encourages cell attachment, differentiation, and proliferation. So there are many different methods to create 45S5 bioglass. One of these methods is the melt, quench, heat, etch technique, in which you start at a temperature of T and quench to create the glass, and then heat treat it to create the glass ceramic, and finally chemically treat it to introduce porosity. So the motivation for this talk was that some commercially available 45S5 bioglass cause bone tissue cells to die on it, which is the opposite of what you really want happening. And there was some bioglass created at Lehigh University, introduced by Moad and Jane in 2008, which introduced nano-macro interconnected porosity through the melt quench heat etch technique that I showed earlier. And on this glass, the bone tissue cells were thriving. And so we were very interested to see what the difference between the two glasses were. And we obtained a sample from the company, and to our surprise, we noticed that the company glass, which is over here, was transparent, whereas the Lehigh glass was pinkish. And we were very interested in seeing what caused this, and we tried to vary the different parameters in the melt quench technique, and determined that if we vary the melting temperature, the cooling rate, and heating rate, etc., we were able to make glass that was more transparent, much like the company glass. So we also wanted to find out if there was a different composition of the two glasses to make sure that we were comparing the same material. And so we did some X-ray photoelectron spectroscopy, and the results are highlighted in yellow. And you can see that there were no significant differences found in the composition of the two glasses. So what really is what's causing the two glasses to be so different in color and such? And so we did some SEM imaging, and we found that the company glass, which is this top image, has this droplet phase separation. A zoomed up picture, it's kind of hard to see, but it's there. So this company glass had this droplet phase separation, whereas the Lehigh glass had a very characteristic nodal phase decomposition type of phase separations. You can see the worm-like structure in the SEM image. So we wanted to study the crystallization kinetics of these bioglass, the two glass, the Lehigh glass, and the company glass, because understanding the crystallization leads to controlling the porosity introduced after when this glass is heat treated for creating bioglass scaffolds. So the method that we used to actually do this experiment was the differential scanning calorimetry. We created different sample sizes using a ball mill and used a sieve shaker to differentiate the different particle sizes. We did this to differentiate surface and bulk crystallization mechanisms. And so the four different sizes that we used in this study were bulk glass, 300 to 500 micron particle size, 150 to 300 micron, and less than 32 microns. For the DSC, we used 20 milligrams of the sample, and of course, the final goal of the study was to determine the crystallization kinetics of the bioglass. So this slide shows characteristic DSC curves for the two bioglass that we found. Just an overview of the DSC. We have two peaks here. The first peak, which corresponds to about 550 degrees Celsius, shows the glass transition of the bioglass. As you can see, both of them have the same glass transition. And the second peak, the exothermic peak, shows the crystallization of the bioglass. Now, I just want to tell you that the green line and the red line show the smaller particle size, the less than 32 micron and 150 to 300 micron particle size for both the graphs. And the blue line and the pink line show the bulk particle size for the two graphs. Now, from these two graphical data, we can see three different points. The first point is that the temperature of crystallization for the smaller samples, the less than 32 and 150 micron, is less than the crystallization temperature for the larger samples by about 30 to 50 degrees Celsius. This is true for both the droplet and the spinodal glass. We also see that for the larger samples, the 300 to 500 and the bulk glass, the temperature of crystallization for the spinodal glass is less than the temperature of crystallization for the droplet glass. And similarly, for the smaller samples, 32 micron and 150 micron, we see that the onset of crystallization is about the same for both the different types of glasses. So to determine the crystallization kinetics, we first need to find the activation energy of crystallization. And our group did this by creating Ozawa plots for the different particle sizes and the different bioglass. So the Ozawa plot relates the log of the heating rate versus 1,000 over temperatures. We used 5 different heating rates, and we were able to find an Ozawa plot like this that I'll show you. So what the Ozawa plot shows us is that the slope of this curve gives us the activation energy of crystallization times the gas constant for different alpha, where alpha is the fraction crystallized, which is determined through the area underneath the crystallization curve. Now, once we average the slopes and multiply by r, divide by r, we can get an average activation energy of crystallization. So this slide shows the 4 different particle sizes, the bulk, 300 to 500 micron, 150, and 32 micron particle sizes for the spinodal glass. I'm not sure if you guys can see very far, but the activation energies are shown here. I'll show them in a summary slide soon. But the point I want to make on this slide is that we saw that as the particle size decreased for this spinodal glass, the activation energy of crystallization actually increased, which is actually not what we expected, because as the particle size decreases, the surface area of the sample should increase, and therefore we should get a lower energy of nucleation, and therefore a lower crystallization activation energy. And so we were a little confused about this, and then we saw a similar trend in the droplet-like glass, but it wasn't as pronounced as the spinodally phase separated glass. And so this is a summary of the Ozawa plots that I talked about. Now there are 2 different things I would like to point out in this summary slide. The first thing is that there's a big discrepancy between the activation energy of crystallization for the bulk glass for both the spinodal and the droplet glass. The difference is about 80 kilojoules per mole, and we think that this is attributed to the fact that the Lehigh glass has spinodal phase decomposition, so it's easier for particles to rearrange, whereas the droplet glass has a very distinct boundary, so it's harder, it'll take more energy for the droplet glass to rearrange. And the second thing, this of course is a hypothesis, and you have to do more tests to quantitatively determine that that's actually what happens. The other thing that I want to point out is that, once again, as the particle size decreases, the activation energy of crystallization increases for both the bioglass. And we, as I said, this was counter to what we first hypothesized, because the nucleation energy should decrease as the particle size decreases. But because the temperature of crystallization is lower for the smaller particle size, we think that that is what causes the activation energy, the rearrangement takes more energy to occur. And this is of course also a hypothesis, because, so finally we got to the crystallization kinetics of our 2 bioglass. To determine the crystallization kinetics, we use the JMA model for nucleation growth for non-isothermal conditions. Now there are 2 two conditions that have to be satisfied for this model to be true. The first is that the entire nucleation process must take place during the early stages of the transformation and has to become visible afterwards. And secondly, the overall crystallization rate is only defined by temperature and not by previous thermal history. A mathematical model of the JMA, a mathematical representation of the JMA model is shown on the bottom of the screen, where alpha is again the fraction crystallized, and m is our JMA parameter, which tells us about bulk crystallization and surface crystallization. So to first see if we can use the JMA model, we have to see if the two conditions that I mentioned earlier are satisfied. And to do that, we use this method proposed by Malek et al. And Malek derived this function z, which is a function of kinetic parameters and temperature. And he said that the maximum of the z of alpha curve should occur at alpha equals 0.63 plus minus 0.02. So we did exactly that when we determined the z of alpha curves for the different particle sizes for our Bioglass. And I just want to say that the open symbols correlate to the larger particle size greater than 300 microns, and the closed symbols correlate to the smaller particle size less than 300 microns for both graphs. So when we calculated the maximum of the z of alpha curves, we saw that both for spinoli separated glass and the droplet separated glass, the maximum of the z of alpha curve was not in the range of 0.63 plus minus 0.02. It was actually 0.56 and 0.55 respectively. And so we determined that the crystallization kinetics of these two, the larger size Bioglass, could not be described by the JMA equation. We also see that the smaller particle size for droplet phase separated glass can also not be described by the JMA equation because the maximum of the z of alpha curve is not within the given range. However, what was interesting is that the z of alpha curve's maximum for the spinoli phase separated glass for smaller particle size is actually in the range that can be that satisfies the proposed model by Malek, and then so therefore it it satisfies the JMA conditions and can be described by the JMA model. We determined the parameter m for this glass, and we determined that n equals 1, and therefore we have 1D surface crystallization for the smaller size Bioglass for spinoli phase separated Lehigh glass. So in conclusion, the type of phase separation has a pronounced effect on the physical property of 45S5. As we saw at the onset of crystallization, for bulk crystallization mechanisms, we saw that the temperature of crystallization for the spinoli phase separated glass is less than the temperature of crystallization for the droplet phase separated glass. We also saw that for the surface crystallization mechanisms, the temperature of crystallization for the spinoli phase separated glass is about the same for the temperature of crystallization for the droplet phase separated glass, which was seen in the DSC data. Finally, we also saw that the temperature of crystallization for the smaller particle size is less than the temperature of crystallization for the larger particle size by about 30 to 50 degrees Celsius. Secondly, we determined that the activation energy of crystallization increases as the particle size of the Bioglass decreases, which of course I had a qualitative explanation for this, but more work has to be done to determine quantitatively what exactly goes on in this situation. And finally, we determined that the JMA model is only valid for particles less than 300 microns in size for the spinoli phase separated glass, which led us to conclude that we have 1D surface initiated crystallization for this glass. Now this information can be used in further studies to better control the porosity of the Lehigh Bioglass. Thank you very much for your attention.
Yeah, normally the phase separation would be associated with the If there is a phase separation in the glass, normally the glass community has seen that the double DG. But in your case, there is no double DG. How do you say that there is a phase separation?
We attributed the phase separation to the images from the SEM, and we only saw one PG.
It's really all interesting, but really complex to understand what's going on. But just going to perhaps discuss this later on with you. But I'm puzzled because since the glass compositions are very similar, you show that they are very similar. Why they have such a different kind of phase separation kinetics? One is spinodal, the other one by nucleation growth. And second, even if you had phase separation by spinodal decomposition and the other one by nucleation growth, in the end, if you look at the miscibility gap, in the end, you end up with the same matrix phase composition, the same composition for the particles in the end of the process. And these are large, these are kind of large. I've forgotten the scale that you had there, but
For
no, the microstructures. Micro.
yeah, these are microns and tens of microns, and this is 500 nanometers.
Yeah. Well, anyway, this is really complex. I think that we have to discuss later on.
But it is known that for the same composition you can get spinodal or binodal. It just depends on your cooling rate.
No.
That's the thing. I don't know. The ones make big blocks. It's low cooling rate. You make small samples. So in the lead borates, that's the daily job there. You get both for the same composition, starting
So
composition.
it depends on the cooling.
It depends just on the cooling rate.
Yeah, but they are the same size of samples, roughly.
I don't know.
No, they showed that the size of samples are similar, so they.
But it was cut from a block, a big block from the company.
Oh, they.
I don't know.
From a big block.
Yeah.
Oh, maybe you're right.
Maybe.
Yeah, maybe you're right.
Oh yeah, he can be first.
Yeah.
Well,
No, actually, the sample, if you look at the figure with all the samples, yes, the company glass they made in a large chunk, that is true. But if you look at the other sample of the same size, these are all made at Lehigh. So we know exactly how it is made, and what we're trying to say, that you control the melting temperature, then the cooling rate, you can control what kind of phase separation you like to have. You know, so it is clearly, and it is phase separated, we see in SEM directly. And we are able to, if you take the glass on the left-hand side, made at Lehigh, which is not pinkish, and the pinkish color, you know, people were suspecting earlier that it has to do with some impurities, but it's nothing to do with impurities, it's strictly the scattering of light. You know, and you see scattering of light more clearly in this spinodal glass than you would see in binodal phase separation.
Thank you.
Another comment? That's not the case, and we thank the speaker again.